Okay, so it appears that we are live. Let me just make sure we switch to the correct slide. Okay, so I think after the longest time, we are back to probably, hopefully, a short and sweet miniature. But nevertheless, an important one because it introduces the so-called Schwartz-Zippel lemma, although I think that should have more attributions, if I'm not mistaken, but I'm just going to go with Schwartz-Zippel. And it turns out that
Lipton, I
that's
think.
yes, at least, and perhaps even more. I remember reading a blog about it that came up with multiple attributions, so I'll hopefully see if I can link to that. But Lipton, indeed, and so yes, we will. It turns out to be a fairly general, fundamental idea, and it will be useful at least a couple of miniatures more from just what I've skimmed so far. So, all right, let's get started and enjoy this one. So, we're going to be again building on ideas that we have seen before, but nevertheless, just to keep it self-contained, let me start with this reminder that a matching in a graph is a collection of disjoint edges. So you can look at the highlighted edges here, and you see that no pair of them overlaps. So that's a valid example of a matching. However, perfect matching is a matching that actually touches every vertex. And oops, sorry, I was just trying to get to the chat. Manu, yes, I'm speaking. Let me put that in the chat. All right, I'm assuming folks can hear. All right, so great. All right. Hopefully that works out for Manu in a bit. So a perfect matching would be one which actually touches every vertex. And this, as you can see right now, is not a perfect matching because there are vertices left out. This one here, this one here. And in the miniature, we are encouraged to find one which is in fact a perfect matching. Now, to be honest, I've not tried, but it looks like it should be doable. No? So we do know that perhaps we have to take this one out because if we yeah, I mean if we pick one of the other two edges from this triangle, we're going to have to leave somebody out here, so that wouldn't work. And then I suppose you could alternate around the cycle and match the guy on the inside to this fellow here. And other than that, just go around the cycle. I think so. Something like this, I think, should be reasonable. Hopefully, that covers all the vertices. But the red edges here are also disjoint from each other. No two of them share a vertex. This is also a valid example of a matching. So, so matching is just that, a collection of disjoint edges. So perfect matching is a collection of disjoint edges that actually accounts for all the vertices in the sense that every vertex belongs to one of the edges, exactly one of the edges in the matching, right? And we're going to focus on bipartite graphs, although you could probably push this narrative to beyond bipartite graphs, but we are going to try and find perfect matchings in bipartite graphs. And a bipartite graph, you might remember, is a graph that can be split into two parts, such that all the edges go across. So these parts are what you would call independent, in that all that means is that there are no edges within the parts. All of them go across. And these parts have to have the same size for us to have any hope for this graph to have a perfect matching, because if the sides are imbalanced, you won't be able to, you will necessarily leave out a few vertices on the larger side. Again, probably needs to be qualified with things like assuming the graph is connected and so on. But if you have, yeah, okay. So basically, hopefully it's clear that you have to have a balanced graph to have a perfect matching. So that's the sort of thing that we are looking at. We're looking at bipartite graphs that have the same number of vertices on both sides. And if you remember yesterday, was this yesterday? I think it was yesterday. We looked at this bipartite adjacency matrix where we pulled up basically rows and columns being indexed by vertices of these two parts. And we have a one exactly when there is an edge between the vertices representing the corresponding indices, right? So if you look at the ith row and the jth column, you throw in an edge if the ith vertex in one part and the jth vertex in the other part are adjacent. And of course, you have a fixed ordering and labeling and so on to go by. So notice that perfect matchings in bipartite graphs can really be thought of as permutations. So for instance, we've seen this graph before. We know that it has a couple of perfect matchings. So I think in retrospect, I should have highlighted them, but here is one of the perfect matchings. We have 1 going to 3, 2 going to 4, 3 going to 1, 4 going to 2. And 5 going to 5. Okay, so this is one perfect matching, and you can read that off as a permutation. In fact, we identified the permutation also in the matrix, and we saw that it was something that would manifest as one term in the product formula of the determinant, right? And we're going to continue working with that idea. But our goal here is to basically check if this graph has at least one perfect matching. I think when we were working with this last time, which was whenever it was, I think we were interested in actually, so we were looking at the number of ways of tiling a chessboard with dominoes. So since that was a counting problem, we were actually trying to count how many matchings were there. Today, we are going to work with the more relaxed question of, is there at least one perfect matching? So we don't want to count all of them. We just want to know if there's at least one. And of course, you could say, well, okay, so the permanent, as we have seen, is just the sum of all the permutation entries without the sign of the permutation. So that would exactly count the number of matchings. But now all we want to know is the permanent non-zero. That's all that we care about, right? So anyway, so the main idea here is to well, instead of trying to directly calculate the permanent or the determinant, so the determinant can also be misleading because, as we saw, terms might cancel. So it could be that you have an even number of perfect matchings, but they all manifest as permutations with opposite signs somehow. And you get a zero determinant, even though your graph does have perfect matching. So that can happen. You will be lucky with the determinant if your graph has an odd number of perfect matchings, because then you won't get a perfect cancellation of the non-zero terms. But with an even number of perfect matchings, the determinant could be a little bit misleading. So we're going to try and do this another way. So the last time we saw this, and we were actually working with the issue of even counting the perfect matchings. We went through this whole circus about, trying to work with signs in a way that actually hang on to all the matchings and cancellations don't happen at all, and so on. Today, we're going to be looking at a different approach, and one that turns out to be just really clean and will lead us to a randomized algorithm for detecting if there is a perfect matching with high probability. So the really clever idea is to say that instead of working with this 0-1 matrix, I will work with a matrix which has zeros whenever there are no edges, same as before. But when there are edges, I will just denote those entries with variables. So something like this. So instead of the ones, I have these variables, and the determinant now becomes a multivariate polynomial. Okay, so you just write out the determinant as you normally would. And notice that, okay, so maybe let me ask this. How many terms will the determinant have in terms of the number of perfect matchings in the graph? So if the graph has like 5 perfect matchings, how many terms will be there in the determinant expansion? So notice that the determinant is now a polynomial in at most n squared variables. Not all of the variables are necessarily present, because if an edge is missing, then the corresponding variable just doesn't make an appearance. So also, I don't know, just to maybe recall the product form of the determinant. So the determinant of this matrix is going to be a sum over all permutations. So IMSM, so all permutations of 1 to n. And for each of those permutations, you will have to take a product. Let's say I going from 1 to n. So from the ith row, you pick out the p-ith column and you take a product of those n terms. That's going to be one term in this sum. Now, some of these terms will not survive. So if you hit a 0, if you're unlucky and you hit a 0 at any point, so for instance, let's look at the identity permutation. That term is going to vanish. It's not going to show up in this polynomial, right? Because that term is a 0 term. It's going to be other permutations that vanish as well. So, for example, I don't know, if I pick this one, these guys, that's also 0, right? You could pick something that's almost there, but still 0. So let's see. So we pick these 3 and these 2. So that's the product of 5 terms, 4 of which are non-zero, but the last one is a 0. So these are all the 0 terms. But some terms do survive, and the only 2 terms that survive are actually written out at the bottom. But in general, if you had a matrix which was defined in this manner, so the ijth entry is xij if ij is an edge, right? And it's 0 otherwise. How many terms survive in the determinant expansion? Considering what you already know about the permanent, for instance. Okay, so I do hope that the question is clear in the sense that I'm not looking for a number, or I'm not looking for this as a function of n, for instance. I just want to know how many terms in terms of some quantity in the graph. And in particular here, since we're talking about perfect matchings, can we say something like the number of terms in the determinant expansion that are non-trivial correspond to something in the graph? And again, not an expression in terms of n, but just a structural quantity. Okay, maybe I'm not posing this question right, or something about the way the definition is. I'm not sure. Okay, so Jagdish, although I think you've sent this message only to me, the number of non-zero terms is equal to the number of perfect matching, and that's exactly right. Every perfect matching contributes a non-zero term, and every non-zero term corresponds to a perfect matching, right? So hopefully that was clear. Maybe what was not clear is what I was looking for, but okay. So let's see. At least in this example, hopefully it's clear that I think we have seen from before that this graph has exactly 2 perfect matchings, and those are the 2 terms in the determinant that survive. And the product is written in a funny order, but just ignore that. It's exactly these 2 things. But okay, in general, the number of terms that you have in this polynomial is going to be equal to the number of perfect matchings. And in fact, yeah, let's just maybe write this out. I'll pull the matrix back up. Yeah, that should have been there right in the beginning. Okay, so this is, yeah, so basically we have the sum of products that we just saw. And notice that if you're looking at, right, so if you're looking at this term here, and one of these things, right, some I comma pi of I is not an edge, then that term just gets killed. along with, takes the sign with it, the whole term gets killed. But on the other hand, if pi corresponds to a matching, then each of these terms corresponds to some variable, and that entire product of variables will surface in the sum, right? And so, but the only pi's for which this happens is when the pi corresponds to a perfect matching. So is this reformulation, this thing about the determinant, is this clear? That this determinant is really a sum over permutations that describe perfect matchings, and it's variate polynomial, therefore. Yeah, this is, yeah, good. Okay, all right, thanks. Yeah, so hopefully this is clear, and this is kind of foundational to what we are going to say next. So if there's any confusion about this, and okay, so I mean, I don't know about you folks, but for me at least, I think the first time I heard about this in a lecture, it just kind of blew my mind, because this idea of, so again, maybe it's a very standard thing, I'm not sure, but plugging in variables inside this matrix, and, you know, kind of expanding that into, like, really thinking of the determinant now as a multivariate polynomial, I thought was like, yeah, this is really curious idea for me. So it wasn't, all I'm trying to say is this wasn't obvious at all what's going on here, because at least until then I was used to seeing matrices that have entries from, I don't know, it's just typically numbers, something from a field or whatever. And just to see these kind of variables being stuck in there and hanging out was kind of strange. So I don't know if, yeah, so if that strikes you as...
No, so this is a standard thing when you do graph isomorphism and stuff like that, in good old days especially.
Right.
So people would actually put variables like this and then somehow figure out the two graphs are the same because they have similar polynomials of similar structure and so on.
Correct.
That was a long time back. I think that is probably what inspired, I think this is by Lovász, and that's what I think inspired him. So.
Oh, possibly. Okay.
Maybe,
right.
yeah.
Yeah, interesting. That's nice to know. Yeah, I mean, perhaps after you, yeah, maybe encountered it a few times, you can go, man, this is standard, but this is, well, I don't know. I mean, yeah, I mean, at least seeing it for the first time, I think it seems like a slightly unusual thing to do. And I think all the cleverness in what we are going to see here is basically this idea of using these variables. And indeed, and I think, yeah, like when I pointed out, there are probably contexts in which you do this sort of thing all the time. So maybe if that's a familiar context for you, this doesn't strike you as being unusual. But if there are others like me who find it a bit weird, then yeah, welcome to the club. That's fine. That's fine too, I think. Okay, so now the determinant is this cool multivariate polynomial. And we just made this claim. I don't know if we made it explicitly, but let's make it explicit now. This polynomial is identically zero if and only if G has no perfect matching. This is the claim. And one direction should kind of strike us as obvious. If G has no perfect matching, I don't know why there's a grammatical error here, and this is thanks to copy pasting. Sorry. So I think G has no perfect matching at all. No perfect matching, ignore that. G has no perfect matching. But if G has no perfect matching, notice that this guy here is basically an empty sum. So if G has no perfect matching, this polynomial is just the zero polynomial. That's visibly true. On the other hand, I want to say that if the polynomial is identically zero, G has no perfect matching. We can prove this by the contrapositive. So what would the contrapositive be? The contrapositive would be, well, we want to show P implies Q. The other way of showing that is that not Q implies not P, right? So if G has a perfect matching, then that A is not identically zero. And to show that a polynomial is not identically zero, it's enough to produce one valuation, right? It's enough to demonstrate one set of values that your variables can take for which the polynomial survives. It's not zero, right? So it's enough to do that to say that it's not identically zero. So what can we do? Well, if G has a perfect matching, it has at least one. So corresponding to that perfect matching, there's a permutation pi, right? So let's just say we set x1 of pi 1 to 1, x2 of pi 2 to 1, xn of pi n to 1, and everything else we set to 0. So at least this term will survive, right? Either as a +1 or a -1 term. So if G has a perfect matching, then this determinant is not identically 0. There's at least one valuation where it survives as a polynomial. Is this clear? Give me a +1 in the chat if this makes sense. Okay, great. So great. So now we have this polynomial with this very useful property. That it's identically 0 if and only if G has no perfect matching. So the polynomial tells us a lot about the perfect matching status of G. So now we want to know if this polynomial is the 0 polynomial or not, right? So one way to do that is to write out the matrix and then write out the polynomial and figure out if it's identically 0 or not. But even writing out this polynomial is kind of an expensive affair, because you can imagine that this is a sum over n factorial terms. And in general, like we said, the number of terms in this polynomial corresponds to the number of matchings. You could very well have a graph where there are exponentially many matchings. In particular, if you had, for instance, the complete bipartite graph, each of these n factorial terms would actually manifest, right? So writing out the polynomial is not such a great idea. I think that would be seriously expensive. So we don't want to do that. But instead, this determinant is like a black box, right? So determinant can be computed quickly. And we can try plugging in values for these xij's, computing the determinant, and hopefully getting some clues about whether the polynomial is an identically 0 polynomial based on the values it takes at some places. Now, suppose I plug in, okay, I don't know, let's just say we have some black box polynomial in xyz. Okay, I don't see the polynomial. I don't have direct access to it. I just have a black box where I can supply values for xyz, and the black box gives me the value of p xyz. I want to know if p is the identically 0 polynomial. Now, suppose I ask for what is the value of p at x equals 1. Let's say it's a real, the variables take real values. So y is 3 and z is 10. And suppose the black box says, the value of this polynomial at these places is 9, or something that's not 0. What can we conclude about p? Is it identically 0? Yeah, it's not, right? Thanks. Yeah, so this is not identically 0 because we've literally found a witness, which is evidence that this polynomial is not identically 0, because here is a place where it's not 0. So for you to be identically 0, you'd have to be 0 everywhere. But suppose the black box instead said that at 1, 3, and 10, the polynomial takes value 0. Can you say that it is identically 0? No, exactly, no, because this is just one place where it's 0. But for it to be identically 0, it would have to be 0 everywhere. But let's say you try prodding the black box a few times. Okay, and everywhere the black box reports 0, right? Let's say you prod the black box like 1,000 times and it says 0 everywhere. Can you say it's identically 0 if that happens? Probably. Okay, that's a great answer. Probably, right, exactly. So the idea is that, well, if you keep getting 0 when you prod this black box and you prod it many, many, many times, then your confidence that it's an identically 0 polynomial slowly increases, right? Because you're like, well, if it was truly not an identically 0 polynomial, I'd probably have hit a non-zero instance somewhere. I would have hit some place where the polynomial evaluates to something other than 0. So we're going to try and formalize this intuition, right? So this polynomial is available to us through the black box of the determinant algorithm. So we can efficiently compute the determinant, and we're just going to keep prodding that black box a few times, okay? So the nice thing about polynomials is that either there's 0 everywhere, that's the identically 0 case, or there's 0 almost nowhere, meaning that there are only a few places. So if you're not identically 0, then you're not 0 very frequently. So the hope is that we will catch the we will catch the evidence for the polynomial not being identically zero with a reasonable probability. That's kind of the idea. And let's try to formalize this using the language of what's called the Schwartz-Zippel lemma. And let me just say this for the univariate case first, where this is just the, I don't know what it's called. Is this called the fundamental theorem? Maybe, I don't know. So anyway, suppose we have a non-zero polynomial of degree d, where the coefficients are from some finite field, or some field actually. Now, at how many places can this polynomial take a value 0 if you have a degree d polynomial in a single variable? Like basically we are saying you have a univariate degree d polynomial, how many roots can it have? Yeah, d, at most d. Exactly. So that's at most d. And so basically another way of looking at this is to say that suppose, well, you have some finite subset of this field that you're working with, and you pick something uniformly at random, the probability that you hit a 0 of the polynomial is at most d over s, because, well, there are d bad places, those are the roots, right? And you're trying to, those are the mines that you're trying to avoid in this minefield. But then if you choose a sufficiently large subset of your finite field from which you're sampling, then hopefully you don't hit the mines with high probability, right? So this is the univariate case, which I think we all know and love. We're going to try and extend this to the multivariate case. It's pretty similar, actually. What we are saying is, well, now m-variate polynomial of degree d, coefficients from this field k. And now the question is, how many m tuples are there that send this polynomial to 0? Well, that's going to be at most d over the size of s to the m minus 1. It's a natural generalization. So when we had the univariate polynomial, this was just s to the 0 or 1. And now we have d times s to the m minus 1. The probability that you hit a 0 if you sample from S uniformly at random. Now, S is a collection of, if I think, okay, so S is a subset of our field and we sample M times, right? And these are UAR samples, okay? The probability that we again are stuck with a 0 is at most d over S, d over the size of S, and for similar reasons, because, well, the total sample space is size of S raised to m, right? Because you're picking m things. Yeah, you're picking m things, and the total number of bad events is at most d times size of S to the m minus 1. So basically, you take this and divide it by the size of S raised to m. So that gives you d over S. That's what you get here. Is the statement of the Schwartz-Zippel theorem okay? Because we haven't proved it yet. We will get to that in a minute. But is the statement clear? This basically is trying to quantify this intuition that you won't run into roots often, right? So we want to say that if a polynomial is not identically 0, then for the most part, it's actually non-zero. But there are these few locations which can trigger it to 0. So if you hit one of those, then tough luck. So you want to sample from a large enough space so that you reduce the probability of hitting something non-zero. Does that make sense? Give me a +1 if we are good, or let me know what's not clear. Okay. Okay, thank you. All right. So first, let's just quickly check that this is helpful for the scene with the matchings. So this is what we want to do with the with our matching polynomial. Remember that's multivariate polynomial with n variables. each term in that polynomial is a sum of, it's actually a multilinear term. So the total degree is n, right? And so this Rm, actually I should have just changed that to Rn because we have n variables here. So we have to pick an appropriate field to sample from. So what you can do is just so that you avoid, so these determinant computations involve numbers multiplying. When you're going to sample at random and you're going to run into all these terms growing. So the suggestion is typically to work with finite field FP. So you have, you can find an appropriate P, which is basically at least n. I want it to be at least n just so that I get a decent success probability. So you'll find, so let's see, what kind of probability do I want? So this is D over S. What is D for me? It is n. So let's say I want a success probability of, let's say, at least half, right? So I want to be able to avoid zeros. In case I have a non-zero polynomial, I want to avoid zeros with probability at least half. So I want that the number of roots, the number of landmines in my space is at most half the entire space. So I know that my D is n. So notice that I'm working with, the number of roots, or the probability of hitting a root is at most D over S. So my degree is n because that's the nature of the determinant polynomial. So if I want this to be at most half, then I should pick S to be something like 2n, right? At least 2n. Then this probability, the bigger the field, the fewer the relative density of the landmines, right? So I pick a field with at least 2n elements. So pick a prime between, that you can find a prime between, say, 2n and 4n. So pick your favorite prime in that range. And work with FP, because then when operations go modulo P, or this prime that you have chosen, then your numbers stay contained and small. So that's good in practice for the algorithm. So that's one of the suggestions from the description in the miniature. But anyway, the point is that, pick a sufficiently large enough field that this probability of failure is low enough, but also not like crazy large, just so that your sampling and your other computations are under control, right? So S is a finite subset. I'm suggesting that it's a finite subset of also a finite field. So I'm saying let's work with, interpret this as a polynomial over FP. I think that's something we can always do. Yeah, so hopefully that's reasonable. And by doing this, so by working with a suitably large subset of things, we can drive our error probability down to at most half. And this is a experiment that we can repeat as many times as we want to drive the error probability down to a point where it's negligible. So you can repeat it n times, for instance, if you want, or something like that, right? In general, if you repeat this experiment k times, your error probability will go down to 1 over 2 to the k. Yes. So let's just recap what the overall algorithm looks like. So pick n values for x1 through xn. Pick them uniformly at random from this finite subset of FP that you have chosen. This finite subset has at least 2n elements. That's all that we need for our success probability to be reasonable. So you've picked these n things, evaluate the determinant at this random point. If the determinant turns out to be non-zero, you can go and celebrate because you know for sure that there is a matching. On the other hand, if the determinant returns 0, that's a little bit suspect. It could be because you genuinely have a graph without a matching and it's an identically zero polynomial. It could also be because the graph does have a matching. It is not a zero polynomial. However, you somehow hit a root of the polynomial. But that's a bad event, which happens with probability at most half, right? So if you're a graph that doesn't have a perfect matching, then the output of this algorithm is never wrong, right? Because if you don't have a perfect matching, there's no way that you will manifest a random point at which the polynomial is non-zero, right? If the graph doesn't have a perfect matching, you're always saying no. But on the other hand, if the graph does have a perfect matching, you might miss it if you end up hitting a root. And the idea is Schwarzschild reassures you that that doesn't happen too often. Okay, so maybe modulo some details. Is this reasonable? I've been saying things like, oh, you might as well work with a finite field. But the main thing is that your subset S should be chosen to have at least 2n elements because you're working with a degree n polynomial. And Schwarzschild tells you that you're hitting zeros with probability at most d over size of S. D we know is n. So we want d over size of S to be at most half. So S should be chosen to have at least 2n elements. That's really the only thing. The idea that you work with operations modulo a suitable prime is more of a additional comment to keep the computations under check and to avoid overflow errors and things like that. But you can ignore that, at least philosophically or whatever. The overall mechanics of this idea, this algorithm, is that clear? Give me a +1 if this makes sense. Okay, awesome. So, all right, so cool. Now the only thing that remains then is to actually demonstrate the Schwarzschild theorem. And I'm going to take the case when m is equal to 1 for granted, because that's the univariate case, and you probably know it as a fact already. You've probably seen a theorem. I mean, you've probably seen a proof. That proof, I think, goes somewhat by induction, or there are perhaps many ways of showing it. So, but in any case, I'm going to take we're going to do induction over the number of variables. I'm going to take the base case a little bit for granted. Okay. All right. So that's going to be a starting point. M is greater than 1. Oh, I didn't realize this was such a wall of text. Sorry. Okay, let's work through it. It's really not bad at all. So let's assume that m is greater than 1. We're kickstarting our induction process here. And what we're doing is really isolating our favorite variable, which happens to be x1. And we are thinking of this as a polynomial in x1 and treating everything else as sort of a coefficient. So it looks a bit funny. I wasn't sure what that meant initially. So I wrote out an example here. So suppose you have, like, generally speaking, a multivariate polynomial. Just go and pull out x1 from each of the terms and collect the terms, reorganize the terms and group them according to powers of x1. Okay. If x1 doesn't appear anywhere in the polynomial, just rename one of the variables so that this happens. Okay. Or just work with a different variable. I think that's a relatively minor issue. Let me just assume, without loss of generality, that we have at least one x1 somewhere in this polynomial, right? So group your terms according to powers of x1 as they appear. And in this expression, k is the largest power of x1 that we see. Does this grouping make sense? So you're now going to be thinking of these guys as these other polynomials in x2 to xm minus 1. We're going to be thinking of those as coefficients of x1. So is this expression, or is this regrouping making sense? Yeah. Okay, awesome. All right, so now we are going to go and try and examine these landmines, which are places where the polynomial evaluates to 0. And we are assuming that the polynomial is non-zero, right? So let's group these bad guys into two sets. The first set is R1. So these are all the places where the original polynomial evaluates to 0, but also this polynomial, pk, which is the coefficient of the largest power of x1. So in this example, that would be this polynomial here. So let's say that R1 through Rm is such that it sends P to 0, but if you look at the values of R2 through Rm, it sends this polynomial also to 0. Okay, so we are looking at only such tuples for now, and I want to argue that this is bounded. Okay, so this is bounded simply by induction. Okay, so this is a smaller polynomial in terms of the number of variables involved because we have isolated x1. So I only have m minus 1 variables here. So the induction hypothesis applies, and its degree is, well, what is its degree? The original degree is d, and I've pulled out k, right, from the original degree because x1 to the k is gone. So the degree is also bounded by d minus k, where k is at least 1. So the degree has also dropped. So basically, we apply the induction hypothesis to see that the number of choices we have for R2 through Rm is at most d minus k times the size of S raised to m minus 2, because now we are working with m minus 1 variable. So if you remember, the original theorem says that the number of roots is at most d times size of S raised to m minus 1. D is the degree and m is the number of variables. So just plugging that in, the degree is d minus k and the number of variables is m minus 1. So that minus 1 is m minus 2. So this expression we get from the induction hypothesis. And now R1 is, well, I mean, R1 is free to take whatever values, but R1 is also sampled from S, so there are only size of S many choices for R1. So we can multiply this by the size of S to see that the size of R1 is at most d minus k times the size of S raised to m minus 1, because there's now an additional size of S to account for the number of ways in which R1 can be chosen. I mean, not all of them may work, because it's possible that you pick something that sends pk to 0, but you set R1 to something and the whole thing may not send p to 0. But this is just a worst case upper bound. So even if all the R1s turned out to, you extend your m minus 1 sized vector in all of these size of S different ways, and maybe all of them do send p to 0, what do we know? So this is just an upper bound, but yeah. So is the bound for the size of the set R1 clear? It's basically plugging in the induction hypothesis on the polynomial coefficient for the largest power of x1 and saying that R1 is a free choice. It can be any of the size of S many things in the subset that we are looking at. Yeah. So this is just a count. Let me know if this is okay, and then we will look at the other set of roots, which is R2. Okay, I'm just wondering if I should. Okay, is some part of this counting or the way the induction setup works not clear? Or let me know. Okay, maybe I should just back up a bit and say, here's what we're trying to count. This is the whole set of M tuples. M tuples that send p to 0. And we are trying to say the size of the set is bounded in some way. What we have done is we have bifurcated the set into two parts. One is where when you look at the last m minus 1 things, right? When you plug that into pk, right, which is a polynomial in m minus 1 variables, if I look at the last m minus 1 coordinates, if those last m minus 1 coordinates send pk to 0, then my overall tuple is an R1. Whereas if they don't send pk to 0, then my tuple is an R2. Okay, so this is just a classification of all my zeros into two parts based on how the last m minus 1 values behave when they're plugged into the polynomial pk. Yeah, and pk is simply defined as the coefficient of the highest power of x1 in this breakup that we did. We said we'll go to the polynomial and reorganize based on powers of x1, look at the highest power at x1 and look at the polynomial that accompanies it. That's a polynomial in variables x2, x3, and so on up to xn, right? So if the tail of your 0 sends this pk also to 0, then it gets counted in R1. But if pk survives, but p goes to 0, then those tuples go to R2. And I want to separately bound the sizes of R1 and R2. The total size of the set of roots is bounded as the sum of R1 and R2, the sizes of R1 and R2. So is that clear in terms of what's going on the big picture? So give me a +1 if the definition of R1 is clear. Okay, nice. So now in terms of counting things in R1, we're basically saying, well, how many things can send pk to 0? pk is a lower degree polynomial in fewer variables. So the number of zeros it has, and the number of places where it goes to 0 is bounded by whatever we get by plugging in the induction hypothesis, right? So we have all of these things that, all of these places which qualify, right? And now each one of those I can extend to a full M tuple in potentially size of S many ways, because so now I have these many choices for the last M-1 coordinates that come from the induction hypothesis. But now to come back to R1, this is only M-1 vectors with M-1 coordinates. So I need to pad it with the first coordinate being R1. But for each of these fellows, I have size of S many choices for R1. And maybe only some of them will send P to 0, but who cares? For an upper bound, I just multiply this count by size of S to get an overall upper bound on the size of R1. Does that make sense? And if not, perhaps let me know what part of the argument is not clear. Is it that the induction hypothesis applies, or is it that is the extension part not clear? With the extension, don't worry about being careful about R1 actually being a 0 of the polynomial P along with R2 through Rn. This is really just a loose upper bound. That's all that this is.
So there are two different definitions of R1 here. You have R1 a point and you have R1 the set.
Okay. You mean small R1 and capital R1?
Yeah. So when you say
when I say R1,
I plug in from R1, I mean.
Okay, that's good.
Yeah.
All right. So I think I should say that I'm looking at this tuple here, Rm.
Okay. So there's a question there.
Why are we only going with the polynomial of the highest degree? That's a good point. If the question is, are we losing out on some counts? The answer is that we are not, because this just turns out to be a convenient way to bifurcate things. Perhaps when we see the other half of the argument, I think I had a similar question too when I was reading this, like, why is it useful to go by what's happening here? I had a feeling that it was perhaps answered when we look at like how R2 is bounded, but and could we have done it with any of the, because I think all of these other polynomial coefficients have the exact same properties that I said, except for maybe the coefficient, the constant term, because in the constant term, there is no degree reduction, but it's still a polynomial on a smaller number of variables. So if the induction is only on the number of variables, I think perhaps that would still work. However, maybe we'll have to complete the argument and see if maybe the argument can be repeated with any of these coefficients, or maybe it's useful that this was the highest coefficient. So maybe let's just come back to that in a minute when we have worked with R2 as well. But yeah, for R1, we are looking at these guys. For capital R1, it's all of these tuples here. Where the first entry is more or less a wildcard, and the number of tuples for which this additional condition is true, that pk goes to 0 on just these guys. This part here is bounded by the induction hypothesis, and this wildcard, which is small R1, that has size of S many choices. So each of your each of your objects from the number of objects being given by the induction hypothesis, each of those can blow up into size of S many more things, potentially, once you plug in for all possible choices of the wildcard entry. So that's where you get the final bound for capital R1. Okay.
Can I just take a shot at this for a second?
Yes, please. Thank you.
Okay, so I think all that Nildara is trying to say is think of this as some sort of filter, right, in a programming language. This stuff. This is filtering your points. If you had none of these constraints, you could have chosen anything to be R1 to Rm, and there would be S to the M of them. And now you use this as a filter. And we know that this by induction doesn't have too many zeros. That is D S to the M minus 2 of them, or D minus K, when that quantity is here. Okay, D minus K into cardinality of S to the power M minus 2. Okay, so now let's look at those zeros. These are the bad guys. And now I have a choice of the first coordinate here because this is also a filter. Okay, the first coordinate I have a choice, but how many choices do I have? I have S choices there for one coordinate. So all she is doing is multiplying these two things, and that gives the bound on R1. Okay, at worst, whatever you substitute here these guys may not get filtered anymore. They may all survive, in which case it's a bad filter, but so be it. And that is our size of R1. Okay, I think hopefully it made sense.
Yeah, I think that made the product quite explicit. Yeah, and I think yeah, no, it was certainly very helpful. I'm just hoping that maybe somebody gives us a shout out in the chat to confirm that the bound on R1 is okay, and we can move on to R2. Okay, that's helpful. Thanks. Thanks, Abhinav. So I'm going to switch over to checking out R2. R2 is basically the rest of it, where PK is not 0. So now the tail does not take PK to 0. And here again, we are doing this loose bound on the tail. Okay, so here we are saying that, well, as far as these guys are concerned, pick them however you like. That can be done in size of S to the M minus 1 many ways, as Vinay just explained. He said it for the entire vector, but now we do it for the last M minus 1 coordinates, right? But now the point is that this filter kicks in a non-trivial way, right? So we know that this guy here survives, right? So let's plug in the values of R2 through Rm in P. When you actually have all the variables from X2 through Xm actually take values R through to Rm, then all of them basically become constants, actual constants from your field. And what you're left with is a univariate polynomial in X1, because that's the only thing for which we have not plugged in a value. Right. And this is where I think Jayati's question was, why are we stuck with the polynomial pk? This is because when we plug in values from R2 through Rm, we actually end up with a polynomial of degree exactly k. So I'm just wondering if we had worked with a lower order term, maybe this would have still been true. But anyway, okay, so this polynomial has degree k for sure, because we know that R through to Rm is not sending this to 0. So this term actually survives. And so we get x1 to the k and maybe some blah, blah, blah after that. So this univariate polynomial that we are working with in x1 has degree k, and therefore that has at most k roots. So now each of these s to the m minus 1 things blow up only in k different directions, because R1 now has the responsibility of actually being a root of this polynomial. Otherwise, your first filter will kind of fail, right? So the same idea, you take the last m minus 1 things and you count them. Last time we counted them using the induction hypothesis. This time this is just a loose count, saying this is at most size of S to the m minus 1. So nothing fancy going on there. This is just, all possible m minus 1 length tuples where the entries are from S. But now the question is, in how many ways can you extend each of these to to R1? Like in what ways can we legally extend this to R1? And now, like before, we cannot take a lazy approach and say, R1 can be one of S different things and try all of those. Then we are in bad shape, because then our overall count becomes size of S to the M, which is back to square one. That's just all the possible entries that we can possibly have. So we don't want that. We want a careful count now. But the only things that I can extend this to are roots of this univariate polynomial. So you take your tuple here, plug it in, and you get a univariate polynomial in X1. And now R1, whatever value it takes, it has to be a root of this polynomial, because I know that this whole thing here has to be 0. So R2 through Rm have done their job, and they have not killed some things. In particular, for instance, they have not killed this higher order term, right? So now the entire responsibility is on X1's shoulders, like basically R1's shoulders, to take care of, to knock out the whole polynomial. So the only way it can do that is if R1 is a root of this univariate polynomial. But then there are only k choices to make that happen. So if you multiply those out, the count you get here is k times S to the M minus 1, because k roots and size of S to the M minus 1 was our umbrella count for all the smaller tuples. So that's the bound on the size of R2. And I didn't make an extra slide for this, but if you take this expression and the expression from the previous slide, it adds up to exactly what we want. So let me clear these annotations. So this is k times size of S to the M minus 1. And what we have before is d minus k times size of S to the M minus 1. So if you add both, you get d times size of S to the M minus 1. Yeah, so that's the count for R2. Let me know if the bound for R2 made sense. I don't know if that's an easier argument or not, but both of them are kind of in the same spirit. Isolate the first entry in the tuple from the last M minus 1, and count them in the best way that you possibly can. Yeah, so that's kind of the idea. So combine the counts, and you have your bounds. So going back to Jayati's question of why are we working with the highest order polynomial? Well, here we want to say, so let's say we worked with I don't know, a different term. Then I think when you plug in the values for R through to Rm, you get a polynomial that has potentially, I don't know. I mean, I think if anything, its degree would be less than k, but I don't see that as being, can its degree be more than k? I guess not. So yeah, I'm not completely sure if the same argument will work if we worked with one of the other coefficients instead of the coefficient of the highest order term. Off the top of my head, I cannot tell. So maybe I'll have to take I don't know if others have any comments on this. If you can see a clear reason for why it would be a deal breaker to move to one of the lower order terms. But yeah, no,
it just is getting a better bound. No? You want to know whether the highest degree term survives or not. If it doesn't survive, then the degree has collapsed.
Correct.
Right? Yeah. So you just want to know whether it survives or not. That's about all.
Right. Yeah, I guess.
Any of the lower order things saying being there, not being there has no implication on the degree of the polynomial.
Right. Yeah. If I understood Jayati's...
But the higher order term, highest order term, for example, if whatever this is empty, if that turns out to be 0, this turns out to be 0, then your leading term is not x1 power 7, but probably x1 power 6 or 5 or something. It collapses.
Correct.
This being 0 doesn't mean anything, because if this guy survives and this being 0, there's no bifurcation that you're doing in justice.
There is no bifurcation. Yeah. So for example, if I just...
So if this goes to 0, I want to say I don't care. That was what we did in the previous in R1, right? In the correct slide that you have currently.
Right.
If this collapses, I am prepared to put everything into R1, and I'm prepared to come up with this very loose bound, right? Because for R1, I said everything is fine. I mean, I'm prepared to take everything and say, well, it gets destroyed. Okay. So I'm really very unhappy that this guy is 0. Okay. And therefore, I'm prepared to upper bound it very badly. Okay. On the other hand, if this guy survives, then I have a univariate polynomial. Okay?
Right.
And that univariate polynomial cannot have too many roots, which is the second case.
Right. I think that makes sense.
Yeah.
I think just to be concrete, I think if here, for instance, if we had worked with this guy here, right, the question was, would the exact same argument go through? So if this goes to 0, which is what's happening in this case, the number of choices that we have for R through to Rm is at most this, because we are forced to make this 0. So that's still the induction hypothesis, right? Does it matter that the higher order terms have survived? I don't know, maybe that's a silly question, but this count would still discount bounding the number of choices. So let's say I'm looking at whatever, P2 or P1, P2 here. This count depends on this polynomial being a polynomial on a smaller number of variables. So that would still survive, and I can still do whatever I want on R1, right? Because that's anyway a loose bound. And what's happening on the other side is when this is non-zero, then you're looking at this univariate polynomial, right? Where I at least have a degree 2 term, but potentially I also have higher order terms. Now, if I'm not able to bound those higher order terms, then maybe that's when I'm in trouble. So basically here, okay, so I think, so Jyoti, I think this is combined with what Vinay just said. Let's try to repeat the same proof, but instead of picking the highest order term, I pick x1 squared, right? So this argument will go through exactly as it is, but the bound that I get here will be something like b minus 2 times s to the m minus 1. Now to get a combined bound from the other side, I would want something like 2 times size of s to the m minus 1. But for that, I would need a bound of 2 on the overall degree of the polynomial. But when this guy is non-zero, I know that the degree is 2, but I know that the degree is at least 2. It's also possible that some of the other higher order terms survive, and I may not be able to argue this bound. So this may still be 7, for example. Then this will blow up. Okay, so yeah, I'm glad that made sense. Okay, so that's about it. This is what Zippin turns out to be extremely useful for many other things. And yeah, I think that's more or less what I had for today. And yeah, we're still over the hour, but any closing comments? Okay, so I don't see any more questions in the chat, but yeah, I think this was nice to work through, and we now know a randomized algorithm for finding for quickly checking if a bipartite graph has a perfect matching or not. For the record, the miniature does say that you're probably better off using the deterministic algorithm for this. There are reasonably fast algorithms that can compute maximum sized matchings, even in general graphs, and even faster ones for bipartite graphs. So this is more of a, I don't know, a cool flex, I guess. Maybe this is not what you would expect is implemented as a library function or something. So
yes, I think this was the first application, at least in computer science, that used the Schwartz-Zippel, if I remember. Okay, this was, I think, the lowest paper was on 7980 or something like that.
Oh, I see. Nice.
So this is, I think, the first application within maybe a year of Schwartz-Zippel.
Okay. Oh, wow. Okay.
And it opened the doors for Yeah, I think Sword Zipple is used. It's bread and butter. So
Yeah, floodgates, I suppose.
yeah, there are probably 1,000 papers which use it now. So,
That's true. Yeah. In fact, even the miniatures don't seem to let go of it for a while. So we'll see a couple of other applications at least, even as we go along. But yeah, I think this is a really useful little nugget. And yeah, thanks for both the trivia as well as the help, Vinay, as always. And thanks to everyone for joining in and for being such a sport about staying all the way. So we'll continue our conversations tomorrow and yeah, come back for more algorithmic applications for the next few miniatures. Thanks everyone again. Good night for now.